there is one drawback about cuckoo plot. It's just a plot. So when you do some visual assessment, it's always subjective. Some people say, okay, it's pretty close to a straight line. Some people say, no, I don't think so. They deviate from the straight line. So we need something that will give us a more certain answer, how likely our values came from normally distributed population. And the answer is a normality test. Actually, the statistical tests, the normality test is a part of statistical test or hypothesis testing. It's a topic for the next block. So I will introduce this test in a very simple form, and then we will discuss it a little bit more next time. Okay. So there are several different algorithms that you can use to get the normality test. You can see some of them here. For example, you can calculate skewness and kurtosis. You remember that for normal distribution, skewness should be close to 0 and kurtosis should be close to 3. Okay. You can use some other procedures. The test we are going to use in this course is Shapiro-Wilk test. It's one of the best tests for normality. But let's talk a little bit about what test is actually. Normality test is an evaluation how extreme your sample is, assuming that it came from normally distributed population. Okay, so if population is normal and the sample is taken randomly from this population, how extreme these values are for this assumption. If they're too extreme, then we can't support this assumption. So we see it seems like it's too extreme to be taken from normal distributed population, so we can't use the normality. If it's not too extreme, then we can say, okay, it seems like the sample came from normally distributed population, so we can use normal distribution to describe the sample. Okay. This assumption is called hypothesis. So we have two hypotheses. The first is called null hypothesis, and that's what we believe is correct. Usually null hypothesis is something that is most natural, most expected. For example, if you have indeed some random values, most of the random values in nature are distributed normally. So it's quite natural to expect that these random values came from normally distributed population. And then you have alternative hypothesis. So in this case, alternative hypothesis is that your population is not normally distributed. Okay. And then when you make a test, you either reject null hypothesis or accept null hypothesis. And in many statistical books, you do this by comparing a probability with a certain value. It's called significance value. I will tell you later that you shouldn't do that. Okay, but so far for this particular part, let's use this significant value. But what is a probability? Well, that's a following thing. First of all, in normality test, you compare your empirical distribution, or cumulative distribution function in this case, with a theoretical one. Okay. Every time you take a sample, you remember, every time you take a sample is not fully representative for the population. It's always an approximation of your population. So it means that every time you take a sample, it will not follow the theoretical distribution very close. It will deviate from that. But how far this deviation can be? You can calculate a probability, which is called a p-value. P-value. P-value is the probability to get a sample as bad as yours or even worse if the null hypothesis is correct. So if your sample came indeed from normally distributed population, how likely to get it like you have, or even worse, so even more extreme. Okay. So if this p-value is too small, by saying too small again, it means that like 2, 3, or 4%. So like, for example, p-value, usually we compare it with 0.05 as I said, but we will discuss these details later. So far, you can use this rule. So if p-value, for example, if you get a p-value 0.01, what it means? It means you have only 1% chance to get a sample like you have, or even worse, if your population is normally distributed. Okay. So this 1% is pretty extreme, right? So it's not very likely that your sample indeed came from the normally distributed population. So in this case, we sort of reject null hypothesis. We will say, okay, seems like we can't use normality here. Then I'll show you a couple of examples. I created several samples. In all cases, the sample size is 15, so we have 15 values. And then you can see the cuckoo plot and the p-value. Let's start the first one. So this one, okay. I must say that these values are normally distributed. So I I got them using a special generator of random values, normally distributed random values. And you can see it's not very well fitted by a straight line. You have some extreme values here, okay? But it might happen because the sample size is still not large. It's only 15. Therefore, the p-value is 0.13. So that means that if you repeat this experiment again, 13% chance to get the values like you have, or even worse. So it means they will deviate from this line even in a worse form. So 13% chance. So it seems pretty big chance, because that's very natural to assume that the population is normally distributed. So it's not that extreme, okay? But in this case, I also added an outlier, artificial outlier here. It's this one, and that decreases the chances to 1%. Okay, so it seems like this value is too extreme for random sample came from the normally distributed population. So that's why here we have only 1% chance. So if we repeat this experiment again, only 1% chance that we will have a sample as bad as we have, or even worse. Okay. So in this case, I also have some outliers, and you can see that in this case the p-value is 0.3. So we don't have any problems on this part, but we have now these two guys, and you can see that they deviate from the straight line. But still 3% chance to get a sample like this, or even worse, if the population is normally distributed. So you can think that 3% chance that my sample came from normally distributed population. Okay. Then finally here you have more values that deviate from normality. And in this case, the p-value is 0.02, so only 2% chance. So once again, we will learn how to assess these p-values, how to deal with these p-values in the next block. So far, you can use this rather arguable rule, but it's okay to use it at the beginning. So when you test for normality, if your p-value is less than 0.05, you can't use this assumption about normality. You should use some methods that do not rely on normality. But if the p-value is larger than, equal or larger than 0.05, you can use the assumption about normality.